the Sirens. And first of all, it's not working. Yes. First of all, what are standard Sirens and what are the dark and bright standard Sirens? First, this question is, the answer is, standard Sirens is a source of gravitational waves in which we can make direct measurements of the luminosity distance as the standard candle. So this is the analogy. We have now the standard Sirens. The name is Sirens is because they don't have a source of electromagnetic waves. But if we have a source of electromagnetic counterpart, this standard Sirens is called bright. If not, they are called dark Sirens. This bright Sirens is commonly from the coalescence of a binary neutral star system, and the dark standard Sirens come from the coalescence of black holes. Okay? So, from the general theory of relativity, we know that the gravitational waves have two degrees of freedom, radiative degrees of freedom, that we call H plus and H cross. And if you compute the signals from a coalescence of binary neutral star or binary black holes, you know that the amplitude of the signal is inversely proportional to the luminosity distance. So, and this is what we want to perform cosmology. The order ingredient joined with the luminosity distance that we want to have is the redshift. Only with the gravitational waves, we don't have information about the redshift. So we need another source, another information to get this redshift. And if we have an electromagnetic counterpart from the coalescence of this source, we can use this electromagnetic counterpart to identify the host galaxy. And so the redshift of this galaxy and compare and make a relationship between luminosity distance and redshift in order to perform all the cosmological analysis. One of them is to measure the Hubble constant. Here I'm showing the most famous source of this kind that the LIGO and Virgo could detect. That is the signal GW1708 and 17. That it was coming from the coalescence of binary neutral star system, in which from the electromagnetic counterpart here, this plot here I'm showing the green part here show the sky position of the source from the detection from the LIGO Virgo. And this blue one is a region from the short gamma ray burst, the imprecision in the sky. And looking for this region, it was detected optical counterpart for which was identified the host galaxy in this redshift. This galaxy is the NGC 4993, for which it was measured the redshift 0.0973. And with this source was performed the first measurement of the Hubble constant using gravitational waves. So as we have only one detection of this kind, we want to detect more of this kind of source in order to perform cosmology and look for how would be the constraints that we will have in cosmological parameters using gravitational waves. The late time cosmology, because we are interested in the astrophysical source for redshift up to 2, 3, 4, but this range of redshift, okay? So, the detector of gravitational waves that we have currently is the LIGO, two LIGOs, one in Hanford, the other in Livingston, US, other one's Virgo in Italy, and the other one, Kagra, in Japan. So, the output of this detector have a lot of noise inside it. And it could have a gravitational wave inside this signal. And how can we identify that this signal is present in the output of the detector? This is made using a matched filtering, in which consists of getting the signal multiplied by a template from a theory of gravity, and looking for if this template match with the possible signal inside the source. This match filter is computed as SNR, that is a signal-to-noise ratio. And if this signal-to-noise ratio was above a threshold of 80, is a convenience, so we can be sure that this signal is a gravitational waves inside the output of our detector, okay? This plot shows the sensitivity of the current gravitational waves detectors in function of the redshift in the frequency. And if a gravitational wave signal in Fourier domain is above this curve, so we have a detectable gravitational wave to be detected with these detectors. Here I'm showing the Fourier domain of one of the detectable gravitational waves, GW15 or 914, other already detections. Here this dashed plots in the Fourier domain, okay? And with this current gravitational wave observatories, we can see how would be the possible source that this detector can be get. For example, here I'm showing this region is relating the redshift and the total mass of the source. All the source that is inside this shaded region is detectable source. So here we can see for a binary neutral star system in this mass range, we can achieve with the current gravitational wave detector, LIGO, Vigo, and Kegra, up to a redshift 0.1. For stellar binary black holes, we can go up to a redshift 1, and so on. But as the bright standard sirens that I want to have an electromagnetic counterpart is basically from the binary neutral star system, this range is very low for our proposal to study cosmology with this source. So we want to have more powerful detectors to detect this binary neutral star system up to a redshift much higher, okay? So this is made with the current third generation gravitational wave observatories. We will be in the next decade, the Asian telescope in Europe, here, showing here below. A cosmic explorer in USA, possible in future, LISA, that is not a third generation detector, but is a first space gravitational wave detectors. And same as before, here I'm showing the plot where we can detect this coalescence with these detectors here. You can see that from ICTP telescope and the Cosmic Explorer, we can detect binary neutral star system up to a redshift 6, and this is very good to our proposal of study cosmology, okay? So in this project, in this presentation, I'm going to show some forecasts of using bright standard sirens to be detected with ICTP telescope and Cosmic Explorer to make constraints in cosmological parameters. So what we have done is simulate this kind of detections for a given distribution of detection with respect to the redshift here. And this curve here, this black, is a expected distribution for this kind of detectors. There is expected in some of this reference here. And this plot here, I'm showing the current inference of the uncertainty, the luminosity distance for this kind of source in function of the redshift that was already estimated from some of these reference here, okay? And as we know, the distribution of this kind of source and also the relative uncertainty of the luminosity distance function of the redshift, we can do the simulation of this kind here. You will see a plot of the Hubble kind of plot relating luminosity distance with the redshift. And with this plot, with this detection here, this simulated detection, we can perform the cosmological analysis that we have done with supernova, for example. But with ICTP telescope, it was estimated that for bright standard sirens, it can detect around 100 up to 500 detection in 10 years of observations, okay? So this is the expected number of detection that we will have with ICTP telescope or with the other electromagnetic detector that we will join with the ICTP telescope. So the models the cosmological analysis that we have done with this kind of mock data here, one of them is a Bayesian model selection, in which we are interested in comparing cosmological nested models in order to see how many detection will be necessary to infer that one cosmological model is better than another one. So what we have done here is simulating detection according to the lambda CDM and comparing this kind of data with other cosmological models, the omega-0 CDM and omega-0, omega-I CDM, and you see how many detections it will be necessary to constrain that the lambda CDM will be better than the other ones. And here I show one result compared to lambda CDM with omega 0 CDM in this plot here, and the other one compared to the most complicated model, the omega 0, omega A CDM. And here I'm showing the logarithm of the bias factor in function of the total number of detections. So as we have simulated our data using the lambda CDM as a baseline model, so we want that this curve will be above this line here, okay? So by how many detections will be necessary in order to this curve will be above on the weak evidence or moderate evidence favoring the lambda CDM. In this plot, I'm showing that using the estimated uncertainty in the luminosity distance redshift for the Einstein telescope, we see that for 100 detection, the data will favor the lambda CDM with a weak evidence. But if we could reduce the error in the luminosity distance, for example, with using other detectors, for example, combining the Einstein telescope with Cosmic Explorer or other third generation gravitational wave detector, making a network of 3G detectors. So if this is possible to reduce this up to 20% of the original error, so we can see that we can get better results of the model selection. For example, here we can see that for a 300 or 400 detection, we can get moderate evidences favoring the lambda CDM model, okay? This is one of these results. And here, I'm showing one example of how much we can reduce the error in the luminosity distance using Einstein telescope, Cosmic Explorer, combining the two ones, and using adding a third detector in here. So here, we know that using the Fisher matrix approach, the error in the luminosity distance, the relative error in the luminosity distance, is proportional to the inverse of the signal-to-noise ratio. So if this is correct, so we can make this plot here. In here, I'm showing the relative uncertainty of the luminosity distance in function of the redshift. The blue curve here is the uncertainty expected for the Einstein telescope. The red one expected for the Cosmic Explorer. The green one here is compared to Einstein telescope. You see that the Cosmic Explorer will be better than combining two Einstein telescopes, but if we combine an Einstein telescope and a Cosmic Explorer, we can get this curve here, this magenta curve here. And if we add a third detector, we will get this black curve here. You see that adding more detectors, we are improving the measurements in the luminosity distance. And here I'm showing what will be the best place of putting a third detector in order to get better measurements in the luminosity distance. Using the same Fisher matrix approach, I'm combining an Einstein telescope here in Europe, a Cosmic Explorer here in USA, and I'm looking for the best place of a third detector like AT detector, okay? So I will put a detector here, estimate what will be the uncertainty luminosity distance for 300 detection in there. And this color here is according to the uncertainty, the relative uncertainty of the luminosity distance. So we are looking for the region of the position in this black region here, okay? Because there's the smaller uncertainty of the luminosity distance. So in this plot here, I'm showing that the best place of a third detector is here next to the US, or here in the ocean, but we can put a detector in the ocean. So the best place of a third detector is here in the US, okay? Using Fisher matrix, okay? This is not the complete analysis, but using a first approximation, this is the best place to put a third detector. Another analysis, a cosmological analysis that we can make with this kind of mock data is the cosmography with standard Sirens. So how will be the constraints in cosmographic parameters that we can get with the detection of bright standard Sirens with Einstein telescope? So we know that we can expand the luminosity distance in power series of the redshift, in which each coefficient is a combination of the cosmographic parameters. Here's the H0, the Q0, the acceleration parameter, J0, related to the third derivative of the scale factor, and so on. But For a given cosmological model, for example, the lambda CDM model with these parameters, H0 equal this value and omega m equal this value, we have specific values of the other cosmographic parameters. So the other parameters will have these values here. So comparing the cosmographic parameters, the cosmographic curve of luminosity distance versus redshift truncate in several orders in this series. Using these corrective values expected for the lambda CDM model, we will have all of these dashed curves here, in which the dark one here is the curve related to the lambda CDM model, and the dashed one for the cosmographic expansion truncated in several orders. The blue one for the truncated order up to the first one, there is the Hubble-Lemaître law here, the blue one, and the other ones for the red one for this truncate up the second, the green for the third one, and so on. So how this, the curve will be the better one to perform cosmography up to truncated the series up to the third order, the first order, the second order, the third order. What will be the best truncation to this cosmographic expansion? And we show, computing the relative difference between the original luminosity distance versus redshift curve with the other cosmographic parameters, we want to see, we are looking for the cosmographic curve that less deviates from the original one. And we can see here that the cosmographic curve that less deviates from the original one is the cosmographic expansion of luminosity distance up the third order in truncation, okay? And this, I show the relative difference in percentage. So we can go up to a redshift 0.71 with a deviation, maximum deviation of 1% using the third truncation in the luminosity distance cosmographic curve, okay? So we are working with this range of redshift to perform our mock data. And so perform the Bayesian parameter estimation in order to get constraints in all the cosmographic parameters. And here I'm showing the results of the relative uncertainty in all the cosmographic parameters, blue for H0, red for K0, and green for J0, okay? In function of the redshift. In function of the redshift because increasing the redshift, I mean increase the number of detection up to get one of these values here, 2000 for the dark curves, and for the less detection up to a redshift 0.7 for 125 detection total. The solid ones is the curves related when we are dealing with the relative uncertainty in the luminosity distance for that approximation that we have shown before, the approximation of the relative uncertainty of luminosity distance versus redshift for the Einstein telescope. And the dashed one is that one related when we can reduce the error up to 20% of the original one. So, and this yellow part here, really yellowish region here, show the region when the measurements of the Hubble constant will be better than the ones with the shoes, okay? And we see that we will have better results using the Einstein telescope to measure the Hubble constant and so on. And if we make in that range of redshift the same analysis for supernova, we will have these constraints in the Hubble constant K0 and J0 using the Pantheon data. And we can see here the relative uncertainty in the cosmographic parameters in function of the total number of detections for that range of redshift between 0 and 0.71. And we see that if we achieve a total number of 750 detections, we can have a similar constraint in Hubble constant that those ones using the supernova from Pantheon catalog, okay? And if we reduce the error up to 20%, we can have better results than those ones using supernova data. And in summary, we have here, we have make these following questions in asking and get the answer for each one. The first question is, what are dark and bright standard sirens? And the second one, how can they be detected? And the third one, how they are useful to late-time cosmology, using model selection or cosmography or so on analysis that you want. And the third point is, what are the cosmological constraints to be gathered with third generation gravitational wave observatory. All of this answer was performed here in this presentation. Thank you very much.
Just a comment, actually. So on slide 13.
13.
Yeah, so just a comment. So you wrote lensing barrier.
Lensing barrier.
Meaning that lensing is a noise.
Yeah,
exactly. And
the source of error in the luminous distance.
I just want to comment that right now it is indeed a barrier, but with the future survey like LSST, Euclid, etc., you will have a lot of galaxy catalysts up to redshift 2, but we're lensing the lensing kernel peaks. So you will, in principle, be very optimistic. You could de-lens somehow, so you could be on this barrier.
Oh, okay.
That would be really interesting for the future, actually.
So I also have a question about this slide. So it looks like combining Einstein telescope with Cosmic Explorer does better than having two Einstein telescopes. Could you say a little bit about like what the difference between the Einstein telescope and Cosmic Explorer are? Like why is the magenta dashed line lower than the green dashed line?
Okay, because if you see here in this plot, I'll show you this the sensitive curve for the Cosmic Explorer and the Einstein telescope, blue for the Einstein telescope, and red for the Cosmic Explorer, and you see that the Cosmic Explorer is a bit better than the Einstein telescope. And if you see here, you can see the blue region here is the region of the Einstein telescope and the green for the Cosmic Explorer, and you see that Cosmic Explorer can achieve a higher redshift than the Einstein telescope because just they are a bit better for detecting this kind of source. And this is the reason why in this plot here, I have that the Cosmic Explorer is better than using two Einstein telescopes.
Is that just due to like the design of the detector or the
I'm not sure if because the design of, I mean, maybe because they are very bigger than the Einstein telescope, because the Einstein telescope will have 10 kilometers of size, and the Cosmic Explorer will have 50. I'm not sure. 40.
So the peak sensitivity in the bucket for Cosmic Explorer can be slightly better, but it would be worse at very small frequencies because it won't be underground. But for neutron star, you're not worried about ultra small frequencies. You actually want to see the main span. But of course, I mean, these are projections. I mean, those sensitivity noise curve can change.
Thank you.
Yeah, hold the microphone for that side. Okay. Thanks.
Hi, I have a question about this plot. So you said that
This one or this one?
The one, the right.
The right one, okay.
Another detector to, it's better built in the US or in the ocean?
Yes, because we have less error in the luminous distance.
So you're going to get a smaller error, but wouldn't that select more sources in a specific region in the sky? Like, I'm thinking if you build in Brazil, for example, you would see another region that you wouldn't in the US.
No,
the point you select some more the same kind of sources, like in the same region of the sky, so you would get less sources from this region where in Brazil or in Australia would see. So wouldn't that be,
okay.
I don't know, worse for the
look,
when you have
for each point, one of these 100 point here, this hexagonal point here, I'm simulating 300 detections around the sky in azeotropic form, and this is not have to do with the position of the source in the sky. But if this detection is right above the two first detectors here, because when the detections is upper the two ones will have a much more signal-to-noise ratio. So the combination of the position of the third detector will be favored when they are joined with the 3-1 here, because we will have a much more signal-to-noise ratio when the three detectors are joined together. We have a much more signal-to-noise ratio.
Okay. And so another question: what are two Einstein telescope detectors?
Sorry?
What are two Einstein telescope?
What are the two Einstein telescopes?
Yeah.
This
the
is
same
on
from the triangle.
a triangle.
Why didn't you consider 3?
Sorry?
Why haven't you considered 3 detectors?
3 detectors?
Yeah.
I'm considering one detector consists of 3 interferometers. In this case, I'm considering 2 Einstein telescopes separated, 2 in triangle shape, okay?
In the same place in the sky?
Not necessarily in the same place, because if you see
in the same place, in the same place, Einstein telescope will be built.
near of for example,
detectors.
putting an Einstein telescope here and other next to the first one.
Okay.
But it could be in other places, but the improvement in luminosity will not be so high with the position of the second one.
Okay.
The point is the number of detection, not the position of that one.
Very nice presentation. Thank you. I have a question about the model selection result.
Model selection.
Where you put in whether you compare WCDM or W0 WACDM, you seem to get the same order of magnitude base factors and not penalized for adding an extra parameter for the plot on the right. Is my understanding correct?
You see that have a small difference when comparing the two ones. A small difference, but they are present here. So you see here that the number is 400 detection here, and here is around 300. So you see this difference.
Okay.
It's small, but they are present.
Okay.
Okay.
Thanks.
Okay, let's thank Josiel again. And we move to the next speaker, Pedro from UFES, from Victoria.
Thank you.
So now we leave gravitational waves. We leave gravitational waves aside. We go back to lensing.
Esse aqui tem que segurar?
Eu tenho que botar no bolso.
Pode colocar na bolsa.
Bota no crachá.
Ok. Obrigado.
Já está lá? Se não toca.
Tá, sim. Hi.
Okay, whenever you're ready.
Okay, thank you. Okay, thank you. So first I would like to thank IFT for the opportunity to be here and the accommodation. And today I'll talk a little bit about what I'm working with my collaborator, Oliver Piatella. We're studying a little bit about gravitational lensing. In particular, we're studying the effect of the cosmological constant besides the already